I'd like to talk to you about simple cells. Simple cells were so named in contradistinction to complex cells, and this is terminology invented by Hubel and Wiesel to describe two classes of cells they thought they could distinguish in visual cortex. And the nice thing about a simple cell is that you can predict the cell's response to any visual stimulus by simply summing the responses you record to individual spots of light, and I'll talk through how that works. Now, complex cells, as you might guess from the name, things aren't so simple, and I'll just talk very briefly about them. So just a reminder about on and off regions of a neuron. In an on region, which I've represented here by this red and yellow colours, a cell tends to be activated by bright stimuli. So spots of light or anything that's brighter than the average for that particular image tends to give you action potentials, and anything that's darker than the average tends to inhibit or even silence the cell. In an off region, it's just the opposite. Dark features tend to excite the cell and make it fire action potentials, and bright stimuli tend to silence it. You'll see several different ways of representing on and off regions, so don't be confused by that. Here are three different examples. So the colour code that I used before, and over here you can see how that colour code is used in a real neuron. And then here's a different colour code where black is used for off and white for on. Here there's little pluses and minuses. Hubel and Wiesel tended to sketch out little triangles to represent the off region and little crosses to represent the on region. These on the left are all idealized simple receptive fields. Over on the right we have the biological reality, which, as you can see, is a lot messier, but hopefully you can see some similarities. Like in both of these examples, you have a central elongated off region flanked by two on regions. Okay, so a simple cell is so simple that you can come up with a mathematical model to describe its response. So by response, let's say I mean the average firing rate. On many repetitions, on average, how many spikes per second are we going to get? And that depends on the image in the following way. You have to sum over all the pixels of the image, and for each pixel you have to take the image contrast, multiply it by the receptive field weight, and sum all those up. And then if that's positive, that's great, just leave it as it is. And if it's negative, replace it with 0. Okay, so that might sound confusing. So let's make this clearer with an example. We're going to take a really simple example where the retina is just 4 by 4 pixels, okay? On the left, we have the receptive field function. These green regions show where the receptive field weight is 0. So this is outside the receptive field, in fact. The cell is not sensitive to visual stimuli in these green locations. Then we have an on region where the cell has a receptive field weight of +1, and an off region in blue where it has a weight of -1. Okay, so how does this cell respond to this image? Well, according to the recipe above, we have to go through, and for each pixel we multiply the receptive field weight with the value of the image contrast. So 0 times 0, 0 times 0, we have lots of those. Here we have something more interesting. We have +1 times +1. And we've got 3 of those, so we've got a total of 3. And then here we've got -1 times -1, we've got 3 of those. So -1 times -1 is +1, 3 of those, we've got another 3. And so the total response of this neuron to this image is 6, whatever the units are, let's say spikes per 100 milliseconds. Okay, so actually this image is going to be the one that drives this particular neuron the best. What happens if we invert the contrast polarity of this image? So we're going to make this bar dark and this bar bright, like so. Let's go through again to work out the cell's response. We've got all these zeros that don't contribute anything, and now we've got +1 times -1 3 times, -1 times +1 3 times. So we get a total of -6. But if you remember, because a neuron can't fire a negative number of spikes per second, we're going to just set that to 0. So the cell is actually silenced here. And that's a very typical property of simple cells. They really care about contrast polarity. So if you take an image and then it's photographic negative, as we've done here, you'll usually get a very different response for a simple cell. Okay, let's think of another example image. So here we've got a horizontal bar going across the cell. So once again, we go 0 times 0 and so on, plus 1 times minus 1, minus 1 times minus 1, so that's giving us minus 1 and plus 1, so that gives us 0. We've got 0 times minus 1 and so on. And if you go through this, you can do this in your own time, you'll find that the response of this cell to this image is 0. So this cell is receiving some excitation where this bright stimulus lies over an on region or where dark features lie over an off region, but it's receiving the same amount of inhibition where dark features lie over an on region or bright features lie over an off region. And overall, that excitation and inhibition is cancelling out and the cell is not responding. So this cell actually shows an important property. It's tuned to the orientation of bar stimuli. As we saw, it responded very well to a vertically oriented bar of the appropriate location, but it doesn't respond to a horizontally oriented bar, and that's an important property of V1 neurons.